Hello everyone, we're here today to talk about Container Object Storage Interface. My name is Siddhartha and I'm leading the group behind this effort.
Hi everyone, my name is Krish and I'm one of the maintainers on the COSI project.
Container Object Storage Interface or COSI is a kube-native API for provisioning and accessing object storage buckets. It is complementary to CSI, which is another API, but it is meant for provisioning and accessing file systems and block devices. So let's get started. I've divided the presentation into two parts. In the first part, I'll talk about object storage and how it is a key enabler for cloud-native operations and data management. Then I'll introduce you to our group, SIG-Storage COSI, that is working on bringing this vision to fruition. In the second part of the presentation, Krish will explain the design and architecture of COSI and follow it up with a demo. Let's begin with a story about Google. Google was the original gangster, the first company to become cloud native. They were cloud native even before the term cloud native was coined. When Google first started gaining traction, it was quickly apparent to them that expensive enterprise-grade servers just weren't feasible to scale at the rate at which they needed. Google was going through one of its biggest growth spurts at this stage. These vertically integrated hardware promised reliability and sustained performance under peak load. However, this came at a cost. Software designed to run on these servers did not have to consider hardware failures as one of their main concerns. However, on that off chance that the hardware did fail, a highly skilled technician with the domain knowledge would have to physically visit the server, inspect it, and perform the necessary steps to fix it. The cost of hiring these technicians, training them, and keeping them on the payroll, in addition to the long turnaround time of fixing these servers by hand, was simply just infeasible. Without better options, Google decided to go with cheap commodity hardware and deal with the lack of reliability of this hardware by designing software to tolerate hardware failures. As they say, necessity is the mother of all invention. Google invented a way to write their software such that even if the underlying hardware failed, the overall service wouldn't be down. They achieved this by separating their workloads into two components, storage and compute. These two components were designated to run on different kinds of servers. The storage part was precious, as data is hard to move and impossible to retrieve if lost. So storage was designated for the specialized, expensive, enterprise-grade servers. The number of storage nodes needed was much less compared to the number of compute nodes, so this was still feasible. Now, the data on these servers, it was meant to be accessed over the network by the compute component. The primitives of serving data this way, in fact, laid the foundation for object storage as we know it today. Compute, on the other hand, was an entirely different story. It wasn't just a scaling challenge in terms of hardware resources, it was also a challenge to scale human IT operations and management. Fortunately, compute does not hold any data, so it was literally stateless. What this means is that two instances of the same compute workload were absolutely identical. They could be replaced with one another to tolerate hardware failures, or run alongside one another for increased availability. By going stateless, no special consideration was required in terms of placement of workloads onto nodes, as data could be accessed from anywhere over the network. This made automation easier to build, not just for provisioning but also for management of these workloads. The primitives of managing workloads this way laid the foundation for orchestrators as we know it today, a prime example being Kubernetes. These above choices were made in order to work with commodity hardware. Google definitely made the right choices back then. As we know now, Google hardly ever went down and has never been slow as far as I can remember, and has served the entire planet seemingly without any issues. They literally did it by inventing the concept of cloud nativity. Here is a picture of their first commodity server. It is housed at the Computer History Museum in Mountain View. There is a caption under it containing a condensed version of the story that I just told you. In order to become cloud native, you only need two things: Kubernetes and object storage. This combination is what COSI is all about. COSI is a standard that brings Kubernetes and object storage together. It paves the path for high-scale applications to run in a cloud-native fashion. The COSI interface aims to seamlessly integrate the lifecycle of object storage buckets to the lifecycle of workloads using it. In order to achieve this, COSI has two separate APIs. One is vendor facing. This COSI API provides a common set of primitives for all vendors to integrate with Kubernetes. The other is application facing. This provides a common methodology for all applications to request object storage from Kubernetes. In the second half of the presentation, Krish will go over these APIs in more detail. COSI adds to the benefits provided by object storage. Any workload that uses the COSI API to request and utilize buckets end up automatically becoming portable across object storage vendors that support the same API. Not to mention the benefits of automation that come from utilizing the COSI API. For instance, access management, deletion of resources, credential rotation, etc. are all automatically handled by COSI. Now, I've talked about cloud nativity. I've talked about COSI. Let's talk about cloud native data management. When using object storage systems, especially when you're moving from file systems and block devices, there are important considerations to make. For instance, the latency of accessing data is much higher in case of object storage, since you're going over the network. Secondly, edits. Edits are not allowed in object storage, so you'll be forced to delete an object and recreate it with the added changes. In both cases, you might be concerned about the performance of the system. Even though the object is accessed over the network, the bandwidth that you can obtain from network these days is much higher than the bandwidth you can obtain from drives. These days, 100 gigabit NICs are commonplace, whereas money cannot buy you a machine with enough hard drives to saturate the same bandwidth. There is a threshold in terms of data size after which object storage becomes faster than local storage. This happens when the POSIX metadata ends up becoming the bottleneck for accessing data locally. This can happen if the number of parallel accesses are too high, if the number of edits are too high, if the files are too fragmented, or if just the sheer size of data is very large. Such a limit doesn't apply for object storage. By disallowing edits, it gains the benefits of sequential I/O, which, when combined with broader network pipes, will make object storage outperform local drives. Finally, I hope I've convinced all of you to throw away your hard drives and SSDs and to jump onto object storage right away. To finish off my part of the presentation, I'm going to talk about SIG Storage COSI, my beloved group that is leading the effort behind this standard. We are currently on the brink of achieving alpha status. While this might make it seem like we are an early project, we are already at a point where we have 2 working drivers and most of the basic use cases of provisioning buckets, granting access, deleting, and revoking access working. We hope to achieve beta status within 1 or 2 releases after hitting alpha. If all goes well, we should be able to achieve beta status by the end of this year. Then, we hope to achieve GA status within 1 Kubernetes release cycle after beta. Here are the final statements for my part of the presentation. We have a vibrant community with active contributors. Come and join us, participate in the community discussion, and help us push COSI forward. Thank you, everyone. I hope to see all of you at the next community meeting. Over to you, Krish.
Let's dive deeper into the COSI project. The best place for us to start is with our fundamental goals. First, we want to define a standard interface for consuming object storage within Kubernetes. Second, we want to minimize the friction for vendors. Our end goal is to have turnkey integration, and this means that object storage vendors should be able to easily create drivers for their respective storage solutions. Third, we are prioritizing workload portability. As Sid mentioned before, object storage is really the most natural fit for cloud-native data management. As such, we don't want to interfere with this portability. Workloads should be easily transferable between different clusters with minimal effort from administrators or developers. There are also a lot of implicit goals within an enhancement to Kubernetes. These include security, scalability, flexibility, and maintaining the solid user experience that we've come to expect from Kubernetes. Let us get started then with defining our API for COSI around these constraints and goals. Our first pair of resources is the bucket request and bucket access requests. Together, these allow us to request the creation of new buckets and also request new accesses for any existing buckets. Then, we have the actual resources which represent the backend bucket and another resource that represents a single access point to one of those backend buckets. Lastly, we have the bucket class and bucket access class. The former defines driver-specific parameters used to create the bucket, and the latter is used to provide specific access policies for the bucket. When designing COSI, we drew on similar principles from the Container Storage Interface or CSI project. As a result, we can draw some interesting parallels between the APIs for both projects. Namely, the bucket class and bucket access class are similar to the storage class. The bucket and bucket access serve a similar purpose as the persistent volume, and the bucket request and bucket access request are used in the same way as a persistent volume claim. Let's now shift our focus to the architecture. There are three main components of COSI. First, we have the central controller, then we have our sidecar provisioner, and lastly, we have the COSI node adapter. The COSI central controller is responsible for managing the lifecycle of buckets and bucket accesses. Then we have the sidecar provisioner, which watches for buckets and bucket accesses. The sidecar communicates with the vendor driver for all create, delete, grant, and revoke operations on the underlying object stores. Lastly, the COSI node adapter works on every node. It is responsible for validating that buckets are provisioned when workloads try to access them. It's also responsible for the mounting of connection information and credentials onto workloads and creating the appropriate finalizers to make sure resources aren't deleted from under our nose. We can examine the relationship between objects. Dotted lines here represent where components watch or manage resources, and arrows indicate where resources have references to each other. As you can see here, an application pod will refer to a bucket access request, which contains a reference to a bucket access. The node adapter will access the credential secret through the aforementioned bucket access. Additionally, the controller is watching all new bucket requests and bucket access requests, and it's going out and creating the buckets and bucket accesses as needed. Not pictured here is the relationship between the resources and their respective classes. The classes define most of the driver-specific parameters and policies, and a request, be it a bucket request or a bucket access request, both must have a reference to its appropriate class. The sidecar communicates with the vendor driver over gRPC and protobuf. We needed to define a new specification since CSI primitives don't translate well to object storage. This is because object storage is a fundamentally different paradigm than file and block storage, and protobuf lets us distribute the spec and utilize synchronous client-server communication. Additionally, we can use the extensive code generation made available by protobuf for bootstrapping development and testing. Pictured here is the protobuf description for the provisioner create bucket method in our provisioner service spec that every vendor must implement. Now, let's move forward with a demo of COSI. We're going to go over the create bucket workflow as pictured here. First, we're going to create our bucket class, followed by our bucket request, and then COSI will handle the rest for provisioning our backing bucket. Then, we're going to utilize our COSI provision bucket to run an application within our Kubernetes cluster. All right, let's get started. So first things first, let's validate that all of our COSI components are up and running with no issues. So we can see that our controller and node adapter are both running and healthy. And we can also validate that MinIO as well as the MinIO provisioner and driver are both also running with no issues. So with that, let's proceed to validating our manifests. And as we can see here, we've defined our bucket access class and bucket class for the minio.objectstorage.k8s.io provisioner. If we recall, the bucket class and bucket access class define the parameters and policy for our bucket. We also have our bucket request and bucket access request. Both of these will go out and create our backing bucket as well as our access for that bucket. Our pod then will consume this bucket access request, as you can see here. With that, let's get our components provisioning. So, first things first, let's define our classes. Next up, let's create our bucket request and bucket access request. So we'll see here that our bucket was created fairly quickly. And we can validate that the status shows that the bucket is currently available. And now we can do the same thing for our bucket access. And this shows that our bucket access was successfully created. So now we can get our workload running. So we'll see now that the workload is already up and running and the credentials have been mounted. Now we can validate that our bucket, named sample bucket, has been created in MinIO. If we switch over to our web application, we'll see that there's no images here right now, but we can pretty quickly get started with uploading some images to MinIO. So let's choose our images. I'm thinking we can start off with this picture of some gophers and the Kubernetes logo. So let's say I really like this part. So let's select this square. Let's call it gophers plus Kubernetes, and let's upload this image. If we switch back to the main tab, we'll see that our image has already been created here. Let's add a few more images. I'm thinking you can add this cute capybara here. Let's upload this one as well. And I'd also like to add this cute image of a poro. This as well. And lastly, I want to upload this picture, but only this pink gopher. So now we can switch back to our home page and we'll see that all of our images show up. So just like that, hopefully we've pleased the gopher gods by setting up a web application storing our images on a backing bucket provisioned by the Container Object Storage Interface. Thank you for coming to this talk. Hopefully it was informative and valuable for you. If you're interested in learning more about this project or how to get involved with COSI, check out the container-object-storage-interface.github.io website. Here you can find more information about our weekly meetings as well as how you can get involved. If you have any questions, feel free to DM Sid or me on Twitter or shoot us an email. I promise we're friendly, we won't bite. Thank you again for your time and have a good rest of your KubeCon EU. Bye-bye.